So, chapter 4, homework is due on this, sorry, no, chapter 5 homework, homework number 4, which is the homework for chapter 5, is due on the 7th. Homework number 5 on chapter 6 is due on the 14th. So is the chapter 6 homework is, I miscalculated slightly and made it due later than it probably should have been. I'm not moving the date forward because that will be uncool, but you might want to do it before because we're going to have a test before that date. So we're going to finish chapter 6 this week. We may finish it today, I don't know, but we're going to finish it this week. And then we're going to have a review of chapters 1 through. So we'll finish chapter 6 and start chapter 7 this week. We'll have a review of chapters 1 through 6 on Monday the 7th next week. And then our test on chapters 1 through 6 will be on Wednesday the 9th. Yes. Roughly, yeah. I wrote the review problems and I wrote the test problems, so I wrote both sets of problems. And so they should be relatively similar, yeah. I make sure that I cover the material that I will, in the review that I will have on the tests. So, you are allowed one sheet of paper of notes as a formula sheet. So that's, you can use both sides, but that's like a full-size sheet of paper. Because it saves me from having to provide you a formula sheet. You put down what formulas you think you need. I don't think you need to memorize them. That's not useful. I mean,
you have like a reference or like
yeah, so when I go through the review, I'll go through all the formulas. And those review slides are up on Blackboard. So so again, the review, I'll go through all the review will be a good place to put together the formula sheet and things. And if you want to look at the review slides in advance, they are already up on Blackboard. So let's talk about strings and springs. So we talked about strings last time. Now let's talk about springs. Strings transmit force along their length. Springs do that, but they stretch. And so for springs, like we covered in the lab, there's Hooke's law. Hooke's law says the force of a spring is K times X. So the constant K here is the spring constant. That is just a constant that describes the spring in question. So it varies from random spring to random spring. So it'll either be given to you in a problem or you'll be asked to find it. It's not something you'll need to know. Tyler, you had a question? Nope. Okay. It's not something you need to like memorize the spring constants for various springs because they vary dramatically. If you want a spring with a specific spring constant, you either make it to that spring constant or you buy one with that spring constant. And like what's going to cause a specific spring constant is not trivial. So, but just in general, it'll be something that you'll either calculate like in this problem or like we did in the lab, we measured the spring constant, or it'll be given and you'll be asked to find the force. So an increasingly popular device for improving airflow through nasal passages is the nasal strip, which has two flat polyester springs enclosed. Uh, he's saying something, but I can't understand what he's saying. Now he's on me, yeah. So is this adhesive strip, and it acts like a spring. It pulls your nose open. So it stretches your nose open. So it's two polyester springs enclosed by a tape covering. And measurements show that a nasal strip can exert an outward force of 0.22 newtons on the nose, causing it to expand by 3.6 millimeters. So this strip is pulling outwards with a force of 0.22 newtons, expanding by 3.6 millimeters. If we treat the nose as an ideal spring, we're not actually worrying about the strip. We're worrying about the nose. We're treating that as if it was an ideal spring. So this is, again, the ideal spring. Actual springs could vary from that. What is the force constant of the spring in newtons per meter? And how much force would be required to expand the nose by 4.1 millimeters? So again, your fundamental equation here is that your force constant K, the force of a spring equals K times X. So you can find the force constant in the first part and then use it in the second. Yes. So I guess if you want to be technical about this, there's a minus sign. Because the force will be in the opposite direction to the stretch. If you move out some distance X from equilibrium, the force will point in. You don't need to worry about it. It's asking for the size. So the force constant will always be a positive number. This is asking how much. If you wanted to think about it, you can think about it outward. Also, this is exerting an outward force to expand it. So there's a couple minus signs in there and you get a minus. But yeah, I think let's see how the book does it. The book just tells you that the size of the force is Kx. You don't worry about the direction. I'm not going to be picky about the direction. But strictly speaking, there's some things you might get to where, strictly speaking, the force is going to be in the opposite direction to the stretch. So if you displace it to the left, the force will be trying to bring it back. So strictly speaking with vectors, this will be force of spring equals K, minus Kx as a vector. But here we're just worried about magnitude. So find the force constant. Well, the force constant is just going to be the force over the stretch. 61. Could be. So that's 0.22 newtons divided by 0.0036 meters. Which gives you 61.1, well, just 61 newtons per meter. Because it's 2 sixteenths. So that's part A. Part B is just doing it the other way around. Force equals K times X. So that's 61 newtons per meter times 0.0041 meters. And that gives you 0.25. We did a whole bunch of spring stuff in the labs, so. But I mean, it's just force of a spring is K times X. Next, we have translational equilibrium. So translational equilibrium problems are situations when the net force on an object is 0. And almost always when you have a translational equilibrium, that's what you're dealing with is static equilibrium. When stuff isn't moving. But strictly speaking, translational equilibrium could also be if you had something moving at a constant velocity. But because I like writing problems that make some amount of sense, it's almost certainly going to be not a situation where just nothing is moving. So the forces all have to add up to 0. You have to make really contrived situations to get a thing moving at constant velocity, sort of translational equilibrium. And so it's just easier. Generally, you're going to deal with situations where if stuff isn't moving, all the forces have to cancel out. The sum of all the forces has to be 0. So if you don't know some of the forces, you can figure them out because the total has to be 0. So here's an example. We have a guy holding a bucket in a well. He's not moving it. And you can look at the forces acting on the pulley here, which are tension 1 down, tension 1 down, and tension 2 up. And the forces acting on the bucket, which is the weight of the bucket down and tension 1 up. And you know, oh, and this is actually something moving at constant velocity. It's moving upward at some constant velocity, but it's still in equilibrium. You know all the forces have to add up to 0. So tension 1 will equal the weight. And tension 2 will equal twice tension 1. And you can use these things to figure out the various unknown forces. So here's an example. If a person hoists a bucket of water from a well and holds the rope, keeping the bucket at rest, so everything here is at rest, as in picture 1 here. Next, the person ties the rope to the bucket. So the rope holds the bucket in place, as in 2. So the first one is the bucket is hanging from the rope and the guy is holding the other rope. And everything is still. The second place is both ropes are tied to the bucket. Is the tension in the rope, in this case, pays 2 is the tension in the rope greater than, less than, or equal to the tension in the first case, case 1. So is the tension rope in the rope here greater than, less than, or equal to the rope here? Here, bucket on one, bucket tied to one rope, guy holding the rope on the other side. And here we have both sides of the rope tied to the bucket. Which one has the greater tension? Or are they the same? So which one are you saying is greater? You say the same, you said? You're saying this one's greater?
Yeah.
One is greater. So in this case, the bucket is held up by just the rope. So the tension of the rope equals the weight of the bucket. And then the force at the pulley here will be the weight of the bucket. Times 2, actually, because the guy has to pull down. And then here, we have 2 ropes holding up the bucket. So the weight is split between the 2 ropes, so the tension in the ropes is half. I mean, but when you're holding it, you're effectively pulling down on it.
Yeah, I thought the second case was he was still holding it, it was just tied at 2 points.
No, yeah, no. They're both tied to the bucket. So the second case, the tension will be half the first case, because you have twice the ropes holding it up, basically. Question? Okay. So here, we have one with some angles. So we want to hang a 6.2 kilogram pot of flowers. To do this, the gardener uses 2 wires, one attached at an angle, and one attached horizontally to the wall, and the other sloping upwards at an angle of 40 degrees, and attached to the ceiling. And we want to find the tension in each wire. So, useful fact here, you can break things down into their vertical and horizontal components. And again, because it's static, all the forces in the x direction will add up to 0. All the forces in the y direction will add up to 0. And when we start talking about rotation, turns out all the rotational forces will also add up to 0. The torques will also all add up to 0. There's in fact like a whole field of study of like advanced versions of this kind of problem called statics, which you take if you did engineering. Okay. Fine. So for this, we can break this into horizontal and vertical components. Weight will be mg, so that will be 6.20 kilograms times 9.80 meters per second squared. That's 60.76 newtons. And we can write our equations for the sum of all the forces in the y direction, in the x direction, and the sum of all the forces in the y direction. These have to equal 0. And the sum of all the forces in the x direction, well, that's tension 1 minus tension 2 times cosine 40 degrees, because it's the horizontal component of this. That's the cosine. And the forces in the y direction, this is tension 2 sine 40 degrees minus the weight. So we don't know what tension 1 and tension 2 are, but we do know what the weight is. So tension 2 sine 40 degrees will equal the weight, which is 60.76 newtons. So tension 2 will be 60.76 newtons divided by sine of 40 degrees, which is 94.5 newtons. And then tension 1 will equal tension 2 times cosine 40 degrees, so 94.5 newtons times cosine 40 degrees, which is 72.4 newtons. Any questions about that? You basically, for these sort of static problems, you break it down into the x direction and the y direction. You carefully look at the angles given because they're not always, and draw the appropriate triangles to find the components in the vertical and horizontal components. And then you set the total force in the x direction equal to 0 and the total force in the y direction equal to 0. And then you find which one you can start working with. So in this case, y was the one I could start working with because I knew what weight was and I wanted to find tension 2. And then I could feed that in tension 2 into this equation to get tension 1. Weight. Yeah. So the weight of the flower pot. And I knew what the weight was because I knew the mass, because weight is mg. Yeah. So I took 6.20 kilograms times 9.80 meters per second squared and got 60.76. And I just used that for my weight. And then I rounded when I got to the end. Here, we have a 1.84 kilogram bag of clothespins that hangs in the middle of a clothesline, causing it to sag at an angle theta of 3.5 degrees. And we want to find the tension in the clothesline. I'll give you a few minutes to work this out. Okay, with me raising the spring problem? Well, I will solve this one in general because it's a fairly common situation. Here's how you can approach it. Well, so the sum of all the forces in the x direction, which will of course equal 0, will be tension times cosine theta minus tension times cosine theta. So in this case, they tell you that these tensions are going to be the same because you're just hanging it from the clothesline. So it's effectively a pulley. But even if these tensions were allowed to be different, that x equation would, this would let you know the two tensions have to be the same. So if this was T1 and this was T2, this would just be T1 and T2. Actually, other way around. T2 and T1. And again, T1 would equal T2. But that means our x equation there isn't very useful. So let's look at why. Because this just says tension equals tension. Well, here we have tension sine theta up from the first, from the left side, plus tension sine theta up from the right side, minus the weight. So this 2 times tension sine theta equals weight. So if we're solving for tension equals weight over 2 sine theta, which is mg over 2 sine theta. So in this case, tension will be 1.84 kilograms times 9.80 meters per second squared, divided by 2 times the sine of 3.5 degrees, which comes out to, rounded to 3 significant figures, 148 newtons. It's like 147.6 something. But this situation where two things are at the same angle on either side is fairly common. And in that case, you end up with twice the y component of one of the ropes is the weight, the force pulling down. Any questions about that? So, connected objects. If you have objects that are connected together, when forces act on objects that are connected together, because they're connected together, they have to move together. Because they have to move together, their accelerations are the same. So if you have two objects connected by a string and you know the force and the masses, you can find the acceleration and the tension. And there's basically two approaches you can take to this. Are you okay with me erasing this over here? I'm not hearing any objections, so. So in general, you can write a system of equations. If you look at each object, you can write, the net force equals mass times acceleration. They both have the same acceleration. So you can say, force equals the sum of all the forces equals mass times acceleration. So if we look at object one, force, that big F minus the tension equals mass one times acceleration. And at object two, tension equals mass two times acceleration. And then this is a system of equations. You can solve the system of equations. So if we treat each box as a separate system, we get force minus tension equals mass one times acceleration, and tension equals mass two times acceleration. And then if you want to solve the system of equations, you can substitute in tension here with mass two times acceleration, and you'll get force equals, you get something like force minus mass two times acceleration equals mass one times acceleration. So force equals mass one times acceleration plus mass two times acceleration. So if we're trying to find acceleration equals force divided by mass one plus mass two, and then tension will be just mass two times the acceleration. If you wanted to find that. So you can set up a system of equations and solve the system of equations. Or you can also treat both boxes as a single system. And you can basically go, the sum of all the forces of the external forces equals the sum of all the masses times the acceleration of the system. And that gives you this equation directly, basically. Force equals mass one plus mass two times acceleration. These are the external forces. It's just the string being pulled on the right there. And then the total mass one plus mass two. And that gives us the acceleration of the system. And that can be a quick way to find the acceleration. And then you can say, if you're looking for the tension, just use, again, tension equals mass two times acceleration. So if you treat it as a system, you have sum of all the external forces equals sum of all the masses times the acceleration. So in this case, that's force equals mass one plus mass two times acceleration. So acceleration will equal force over mass one plus mass two. Which is the same equation we got by solving the system of equations. So there's two approaches. They'll both get you the right answer. Just whichever one is easier to you. Sometimes it's easier to think about it as one big system. Sometimes it's easier to think about just a system of equations and how they interact. Additionally, if there is a pulley, in order to make your brain not melt so much, it's easiest to have the coordinate system follow the string. So over here, tension equals mass 1 times acceleration. And then you just bend the coordinate system around the pulley. So over here, weight 2 minus tension equals mass 2 times acceleration. So by following the string, it just becomes easier to think about the acceleration. Because the acceleration horizontally of this mass must equal the acceleration vertically of this mass. So you just treat them both as the positive direction and bend it around the corner. This is particularly useful if you have something like a mass on a slope with a pulley. That can, bending it around the slope can be quite helpful. Oh yeah, this has a weird error in the picture. Ignore the stuff outside of the box for M1. There was a weird mistake in the drawing here. The two masses, mass 1 and mass 2, are connected by a string that passes over a pulley. Mass 1 slides without friction on a horizontal tabletop, and mass 2 falls vertically downward. Both masses move with a constant acceleration of magnitude A. Is the tension in the string greater than, less than, or equal to the weight of block 2, M2 times G? So do you think the tension in this string is that greater than, less than, or equal to the weight of this mass? Anybody have an idea? Tension in this string is greater than, less than, or equal to the weight of this mass. The whole thing is accelerating this way. Anybody have a guess? Yes. Sorry, can't hear you. Equal? That would be the case if it wasn't accelerating. It is less than. It is accelerating in the direction of gravity. So gravity is pulling it down harder than the string is pulling it up. So the tension in the string is less than the weight. So mass times acceleration is going to equal weight minus tension. And that is going to be a positive value. So this thing is falling downwards and accelerating downwards. And the tension in the string is going to be less than the weight. So here, let's work out the actual acceleration and the tension in the string. So a block of mass M1 slides on a frictionless tabletop. It's connected to a string that passes over a pulley and suspends a mass M2. We want to find the acceleration of the masses and the tension in the string. So it's useful to bend your coordinate system around the corner. Weight 2 is pulling down in the positive x direction. The tension is pulling up in the negative x direction on mass 2. For mass 1, it's being pulled forward by a tension because of the acceleration A. So remember, the fundamental equation is that, the sum of all the forces is mass times acceleration. So let's write our equations. Let's look at mass 1. Mass 1, the only force, the net force in the x direction is tension, and that will equal mass 1 times acceleration. And if we look at mass 2, we bend around the corner, we look at the x direction, we have weight 2 minus tension is mass 2 times acceleration. So if we want to find the acceleration, the easiest thing to do is just add these equations. So tension cancels. You get weight 2 equals mass 1 times acceleration plus mass 2 times acceleration. You can also think of this as a system. This is, mass 1 plus mass 2 times acceleration, and the external force is that weight 2. So acceleration is the weight of object 2 over mass 1 plus mass 2. So that's mass 2 times g over mass 1 plus mass 2. And then the tension is just mass 1 times acceleration. So that will just be mass 1 times mass 2 g over mass 1 plus mass 2. Any questions about that? Okay. This is something called Atwood's machine. Atwood's machine has two masses going over a pulley with a string connecting them. And we want to find the acceleration of the masses for general M1 and M2. And evaluate for the specific case of M1 equals 4.5 kilograms and M2 equals 5.5 kilograms. And putting together the equations, it's easiest if you say up is positive for M1 and down is positive for M2. That'll make it the way to find the appropriate forces and such. So in this case, they're each being pulled down with M1G and M2G, and pulled up by the tension. But the acceleration of M1 is up, the acceleration of M2 is down. Problem is easiest to think about if we treat the acceleration as positive in both cases, and just make, the tension is positive in this case, the tension is negative in this case, and so forth. You bend the coordinate system around the pulley, it makes the math a little more easy to understand. Well, I will give you guys another minute, so. I guess I'll get started because no one seems to be writing anything. So the way you can set this up, I'll do it two ways. I'll do it with the system of equations, and then I'll do it treating it as a single combined system. So with the system of equations, our first equation for mass 1, we get tension minus M1G equals M1 times acceleration. And then for mass 2, we get M2 G minus tension equals M2 times acceleration. Because here, X is pointing up, and here, X is pointing down. Then if we add these equations together, tensions will cancel. We will get M2G minus M1G equals M1A acceleration plus M2 acceleration. So if we solve for acceleration, let's simplify each side. We have M2 minus M1 times G equals M1 plus M2 times acceleration. So we simplify, then we can divide both sides by M1 plus M2, and we'll get acceleration equals M2 minus M1 over M1 plus M2 times G. The other way you can do this is treat it as a system. So the sum of all the external forces equals the sum of all the masses times the acceleration, which is m2g minus m1g equals m1 plus m2 times acceleration. So acceleration is again m2 minus m1 over m1 plus m2 times g. So for the specific case of 4.5 kilograms and 5.5 kilograms, that will be the acceleration is m2 minus m1 over m1 plus m2 times g. So that will be 5.5 kilograms minus 4.5 kilograms over 5.5 kilograms plus 4.5 kilograms times 9.80 meters per second squared, which is 1 kilogram over 10 kilograms times 9.8 meters per second squared, which will be 0.98 meters per second squared. Any questions about that? This is the two different ways. Okay. Does everybody have this down? Where the numbers are plugged in? Over here? Okay. So now we're going to talk about circular motion. If something is moving in a circle, it has to have a force acting on it. Otherwise, it would move in a straight line. Somewhere up here, I think I have a smaller weight. Yes. But I'd rather not do that with the 1 kilogram weight and possibly hit myself in the head. Because I have definitely hit myself in the head during this demonstration. So if you have an object moving in a circle, to keep it moving in a circle, it's accelerating. Its direction is constantly changing. To keep this moving in a circle, there needs to be a force causing it to move in a circle. And it turns out the acceleration of this object is the speed it's moving at squared divided by the radius of the circle. That's the acceleration to keep something moving in a circle. We'll go into much more detail about it when we start talking about circular motion. But the force is towards the center of the circle. In this case, the force was being provided by the tension of this rope. So, you spin something around on a string, the force is being applied by the string towards the center of the circle. So there has to be some force acting on this object to keep it towards the center of the circle. And that force centripetal force is mass times the centripetal acceleration. These are just magnitudes, which is mass times the speed squared over the radius. And the direction is towards the center of the circle. So it's radially inwards. So the acceleration is speed squared over the radius. So the force is mass times speed squared over the radius. So this can be provided by a number of things. The tension in a string. If you're on a banked curve, it can be provided by the normal force. Or if you're on one of those rides where you're in that big cylinder that spins and they drop the floor out from underneath you, then it's provided by the normal force. It can be provided by friction. That's the most common case with cars going around corners. There's a number of things. At the top of a roller coaster loop, it can be provided by gravity. So if you're on a roller coaster, when you're upside down, much of the force that is keeping you going in a circle is provided by gravity. Not all of it, actually. If your roller coaster is designed correctly, some of it is also provided by a normal force. But yeah. So here are some examples where it's provided by the normal force. A car on a banked track. When a car is on a banked track, the normal force has a component towards the center of the circle. So you can set up a car on a banked track at a certain speed. So it will just travel around that track without needing any friction from the tires to keep it going. And that'll also mean that it'll steer itself around that banked track because it's like a nice stable state. So there was a thing that people used to do, these test drivers, I don't know, it's some car company. The test drivers were demonstrating cars. They had this big banked track and they knew a speed they could drive the cars around the track so they wouldn't slide down. And so what they would do is they'd get the car up to that speed at the right angle, so it was going around the track, and then they'd turn around with both hands and offer their passenger a cigarette and a lighter. So they aren't touching the steering wheel. Here, for example, when you're going through a dip, the normal force is what's providing the upward force. Now, if an object is changing its speed as it moves in a circle, it will also have an acceleration tangential to the circle. And we'll be getting into tangential acceleration versus centripetal acceleration when we get into circular motion, which will be in chapter 10. So that's going to be a while. So centripetal acceleration changes the direction of motion. Tangential acceleration speeds up or slows down the motion. So we won't have any problems with tangential acceleration until later in the semester when we actually get to circular motion problems. So if we have a 1,200 kilogram car that rounds a corner of radius 45 meters, and the coefficient of static friction between the tires and the road is 0.82, what is the greatest speed the car can have in the corner without skidding? So in this case, the force, the centripetal force, is going to be provided by static friction. Remember that the force for static friction The max is mu static times the normal force. So I'll let you work on this for a little while. So our centripetal force is the force of friction. So we can say that mu static times the normal force equals mass times speed squared over radius. And we can plug in our normal force. Our normal force is just going to be counteracting the weight of the car, so it's going to be mg. So mu static times mg equals mass times speed squared over radius. And then we want to isolate velocity, speed. So we multiply both sides by r and divide both sides by mass. And we will get speed squared equals mu static times m times g times radius over mass. Mass cancels. So this is just mu static times g times radius. So amusingly enough, the mass of the car doesn't actually matter, it cancels out. And so the velocity is just going to be the square root of mu static times g times radius, which is the square root of 0.82 times 9.8 meters per second squared times 45 meters, which is 19 meters per second. Now this is an interesting situation because the static friction is proportional to the mass, because it's proportional to the normal force, which is equal to the weight. In this case, the mass ends up canceling out. And so the speed limit for turning is just a function of the friction between the road and the tires, the coefficient of friction, the radius and gravity, and doesn't actually matter about the weight of the car. The mass. Yes. Oh, centripetal. That's just, it means center seeking. It's just for circular motion. It's specifically that force that keeps you going in a circle. Centripetal, which means center seeking, basically. The force that points towards the center of the circle. Here, if we have a road that's banked at the right angle, a car can round a corner without any assistance from friction between the tires and the road. So we want to find the appropriate banking angle for a 900 kilogram car traveling at 20.5 meters per second and a turn of radius 85 meters. So here, the relevant component of force will be the horizontal component of the normal force. So just in this case, force centripetal is going to end up equaling the normal force times the sine of theta. That's our horizontal. And vertically, the weight, which is mg, will equal the normal force times the cosine of theta. That would be the vertical component of normal force, is going to equal the weight. Okay. So here, we can solve for normal force. Normal force is mg over cosine theta. Then we can plug that over here. Force centripetal is going to be mg over cosine theta times sine theta. So that's mg tangent theta. And then the centripetal force, that's mv squared over r. So if we want to solve for theta, we have mv squared over r equals mg tangent theta. We divide both sides by mg. Mass cancels. We get velocity squared over radius times g equals tangent of theta. So if we plug in our numbers, we get 20.5 meters per second squared over 85 meters times 9.80 meters per second squared equals tangent theta. That equals 0.5045. So theta equals the inverse tangent of 0.5045, which is 26.8 degrees. And I think I'm going to stop there for today. We'll finish off chapter 6 on Wednesday. There's very little left. We're in the last section, actually. And then we'll start up chapter 7, but the test will only be on chapters 1 through 6. Okay? Oh, well.